In this video, we're going to explore the relationship between the standard matrix for a linear transform and the more functional version of it, and also explore how we can use the standard matrix to do what we would usually do by hand with x's and y's, and see if we can abstract away having to use variables at all. It's going to be a very powerful technique, as we'll see shortly. But for now, let's just start with an example. Here we have a matrix that we are told corresponds to a transform L, and we put the A here to give the subscript of, right, the linear transform is defined or aligned with this matrix here, A. As a quick check-in, ask yourself, what are the dimensions of the input and output spaces of L? So we're mapping from real vector space to real vector space, but what's the dimension of each of those? Take a look at A and see if you can remember how that works. The two things to remember are we're doing columns, and each column is an element of the output space. And so that here is R4. So we're mapping into R4, and each column is for one input dimension. We have to have a column associated with each input dimension, so we have 3 of them. That means we're at R3 as the input space. Now let's think about what this A matrix and the values in it mean, not just its size. Remember, A is called the standard matrix for a reason, and the standard is that if we apply the transform of the simplest possible input ranges, so all the first variable, all the second variable, all the third variable, how does that relate back to the matrix A? Well, remember that each column of A is equal to the L of one of these simple, let's call it unitary inputs. It's not really an official word for this, but the inputs which has a 1 in one slot, and they go with the corresponding columns. So L of 1, 0, 0, that's what we're asked to figure out here, is equal to the first column of A. And again, this is in the first element, is the non-zero or the 1 value, and so we get the first column of A back, and then that is simply 1, 2, 4, 0. And you can kind of see where this is going, but we'll do it in detail anyway, just to reinforce the ideas. So here we have the second element, and that is going to correspond to, not too surprisingly, the second column of A. This is a 2, that's a 2. That's how we define the standard matrix. And this is going to give us values of 5, 0, 1, 7. And for the last one, I won't belabor the structure, 0, 0, 1. That's the third element that's non-zero, so that'll correspond to the third column of A. And that will be 3, 8, 6, 0. So again, just referring back to size and dimensionality, we started with a 3-element input, and we end up with a 4-element output. That corresponds to what we said before. We're going to have 3-dimensional vector inputs and 4-dimensional vector outputs. All right, so now let's compute the transform of an arbitrary input value. So in the last one, we said we're going to transform 1, 0, 0, 0, 1, 0, 0, 0, 1. What if we have not 1 and zeros, but x, y, and z? Well, fortunately, because of linearity, we know that is equal to the transform of x times the 1, 0, 0 vector plus y times the 0, 1 vector. Get my parentheses correct here, plus z times the 0, 0, 1 vector. Why? Because this is just a really long way to write out the components of x, y, z as inputs. Again, this could be a vector. Sometimes we get a little short with the vector inputs. If it's obvious that it's just a list of components. But through linearity, again, this is going to be the transform of 1, 0, 0. I'm going to put x afterwards. You'll see why as we go through the remainder of this example. LA of 0, 1, 0, and plus LA times y, sorry. We cannot forget that. Plus the transform of 0, 0, 1 times z. Again, because the function LA is linear, also A is linear, we're going to be able to break the x out, and the sums we can break out as well. And what that's going to give us is those 3 columns. So 1, 2, 4, 0 times x plus 5, 0, 1, 7 times y plus, last but not least, 3, 8, 6, 0 times z. Now that's interesting by itself, but I want to take one last way to reflect this and think about it in a whole long form. So I'm going to take the 1 times the x, so I'm going to do 1 times x, 5y, 3z, and add those up. So 1x plus 5y plus 3z's. Then for the next row, we're going to have 2 times x, 0y, 8z, 2x, 0y plus 8z, and now we've seen the pattern. We're going to get 4x plus 1y plus 6z's, and 0x plus 7y plus 0z's. And that I wouldn't care about particularly, except, oh, it's really, I hope, sounding like something we've done before. Just look at this pattern. I have 1 times x plus 5 times y, 3 times z. Hey, what's another way to write that? Well, if I had the vector 1, 5, 3, and I did a dot product with x, y, and z, that would be exactly what we get for this row. How about the second row? Well, it's 2, 0, 8 dotted with x, y, z. The next row is 4, 1, 6 dotted with x. Ooh, this sounds an awful lot like a dot product. Now we've seen this in a concrete form, let's maybe see how we can tease this out into a general case and make sure the pattern's there, not just for the set of numbers. So what we're often going to do, especially if you've done programming already and work with matrices, you're often going to start with a matrix. You're not going to have a function, you're going to start with a matrix representation of it. And if we want to compute the transform of any new vector input, then we need a sort of process for that. And what we're going to do is define a new thing. It's called a matrix product. And so we have our matrix here, matrix A, and then we have our input vector, V. What we know about the A matrix is that it is the transform of the individual building blocks. And if we expand this out, what we're going to get are the columns of A. So that's what these W's are here. Columns of A times the vector times V's coefficients, if you like. Coefficients or components. And that's exactly what we got in the last example, just with the more abstract terms. We had these columns. Where did they come from? They were the original columns of the A matrix in the matching order to the components of the input. And then the calculation of our output was take that vector, multiply it by your first component of input. Take your second vector here, multiply it by the second component of your input. And last, third component of your input vector. And again, this starts looking more and more like a dot product. I'd argue it looks more like a dot product here because you can see the something 1 times x1, something 2 times x2. So it's a little more complicated because these are vectors themselves. Usually you do scalar, but we're certainly in the same ballpark, which is always interesting to take an idea you've seen and maybe extend it in an unexpected way. So let's see how we can evaluate this kind of transformation for a certain point given the example. So working from the last page, the previous page, what we would say is that if we want to transform the value 2 for -1, we could also write this as, I'm going to put big brackets on here. So we got our A matrix, and then we're going to put beside it our vector 2 for -1, which is what we call V. So this is our AV. And this is what we're using now as a matrix product. Okay. So from the last page, we were told how we can do this. We're going to take the first column of A. In fact, let me break this down explicitly into 3 columns. This was what we called W1 on the last page, W2, W3. And we were told that we can decompose this operation here. Going back a slide. This thing is take the first column and multiply it by the first value or the first component of your input. Okay. First column of my matrix is 1, 2, 4, 0. And we are going to multiply that by x1, which is 2. So this part here goes to there. Then we're going to add to that the second column of A, which is 5, 0, 1, 7. And then for that, it's going to get a multiplier of 4, because that's our input for the second component. Then last but not least, we're going to have 3, 8, 6, 0, the third column of A, and we're going to multiply it by the third component of our input, so -1. And then we just do the matrix math here. So moving across, we have 2 plus 20 minus 3, 22 minus 3 is 19. Then we have 2 times 2 is 4. 0 times, so 4 plus 0 minus 8 is negative 4. Then 4 times 2 is 8. Plus 4 is 12. Minus 6 is 6. And last but not least, 0 plus 28 is 28. 28. So if we're trying to compute, hey, how does this value transform, this vector 2, 4, negative 1, does it transform with this matrix? Well, we can break down the columns, and then we can multiply each of those columns by the input we were given to get the output. And notice this is an R4, so our transform here does map 3 variable inputs to 4 variable outputs, like so. And we put in an x, y, z, a 2, 4, negative 1, and we got back a 4-element vector, 19, negative 4, 6, 28. All right, so that's fine. That's fine. But gosh, this seems like a lot of tedious work. Like why? Yeah, there's a better way. Let me just go with that. There's a better way. This question looks identical, but we're going to operationalize it in a slightly different way. So L of A of 0, negative 1, 1. We just said in the last thing that this is a matrix multiplication of what we have up here, 2, 0, 8, 4, 1, 6, 0, 7, 0. And then we're putting our inputs as a column vector beside that. And we'll see why in a second. Going back to the previous slide, how did the 2, 4, 1 relate to our vectors? Well, we took the first component times the input. First component times the input. There we go. That's a tongue twister. Well, why can't I just do that? Wait, hold on, that was a dot product, right? I took the dot product, so I had 1 times 2 plus 5 times 4. It was the dot product of the 1, 5, 3 with the 2, 4, 1. Hey, we can just do that. We can just do that in our heads if we like. So what we're going to do is a dot product of the first to the first, second to the second, third to the third. Now this is often easier to do if you can see fingers. Usually I'd call this the finger walking method, where you have 2 fingers and you go in A, we go left to right. So for example here, the 1, 5, 3, and then in V, we go top to bottom, which in this case here is 0, negative 1, 1, and take the dot product as you go. So again, dot product is just a short form for saying multiply as you go and accumulate a total sum overall. So what does that look like here? I'm going to take the 1 times the 0. And again, the idea is we can probably do this in our heads. Often we do it with computers, but for this scale we can do it in our heads. 1 times 0, minus 5 is minus 5, plus 3 is 2. Boom. There's my calculation of the first entry of our answer. Let's do that again. So we're taking the dot product now of the second row with this whole column vector here. 0, 0, 8. Next up, this will be more complicated. 4 times 0, 0, minus 1 plus 6 is 5. 0, minus 7, 0. Actually, it's not bad at all. Minus 7. So rather than doing the full expansion that we did in the previous method, so this is the technical way that it always works, and it gives us a nice breakdown of how we're doing our calculation. In practice, we often just think about a bunch of dot products or for loops. Take the first row and this column and multiply it out and see what you get. That'll give you one entry. So 1 times 0 minus 5 plus 2. Then take the second row and this column, and again do the dot product. So again, with 2 fingers, it's easy to kind of walk left to right and walk down at the same time and just match up the individual elements. But we can get a calculation that leads us to this value very, very quickly. Just a quick practice, let's try that over here and just see how it works, perhaps in a more efficient way than what we tried the first time. So if I wanted to calculate the transform of 2, 4, negative 1, I would just write my 2, 4, negative 1 as a column vector here. And then remember that how do we get the resulting value of our transform? We take the 1, the 5, and the 3 and multiply by the 2, 4, negative 1 and add those all up. So 2 plus 22 minus 3 is 19. Boom, we already had that. Then 4 plus 0 minus 8 is minus 4. 8 plus 4 is 12, minus 3 is 6. And sorry, minus 6 is 6. And then 0, 28, and 0. So you don't need to go through this breakdown of the process. You can do it a little more efficiently, one component at a time in your head. And this is going to be the basis for what we're going to call matrix multiplication more generally. So it's worth practicing this early. This is not a shortcut that's only applicable here. This is going to be the start of something more fundamental. Just giving you a heads up about that. All right. With that, we're pretty much at the end of this week. What we're going to look at next week is matrix multiplication, and then how we can use this matrix representation for a transform. Remember, we used to have functions, now we just have a grid of numbers representing our function. How can we work with just this and get back to our basis for the image, basis for the kernel, dimension of the image, dimension of the kernel questions? That'll be coming up soon.